Welcome to this short video on basics of gas chromatographs. Gas chromatography is a very important tool in CO2 reduction because we can have multiple different products and we need to be able to quantify how much we get of the different products. In this video we will look at the more technical part of how the gas chromatograph works and how we analyze the data, what the data means. But let's first have a look of the sketch of a gas chromatograph. Gas chromatographs can look in many different ways depending on the specific use, but this is a schematics of the one that we are using in our lab. So first I will go through the different parts of it, and what you see here is the small black boxes is a lot of gas inlets. These are pressure controllers, flow controllers. In this case, they are all supplied by argon, and they are pushing gas through the system. We also have one supplying hydrogen and one supplying clean air, which is both used in the FID. The FID is a detector, in this case 1 out of 2, both have an FID detector and a TCD detector. They work in slightly different ways, but we'll get into that later. Then we have different valves. In this GC we have 3 valves, and it will be clear what they do in a second. Then we have sample loops, which is a small tube that's just curved around with a total volume of around a quarter of a milliliter, so around 250 microliters. And then we have a methanizer. A methanizer is simply just capable of converting CO and CO2 into methane by running it over a hot catalyst together with hydrogen. And then we have the heart of the GC, you could say, the columns. In this GC we have 3 columns. You should see we have 2 columns and then 1 that's received. There's slightly different working principles. You can find many different columns in the world, many different types of columns, some capillary, some packed columns. The main point of all of them is that when gases go through, different compounds will be retained more or less. Meaning that if we send in our carrier gas, so a gas stream with different products in, the different compounds or reaction products, could be CO, it could be ethylene, they will be retained at more or less, meaning that they will exit the column in different times. And in general, lighter products get through faster than larger products. I should say larger compounds. So it perhaps looks a bit confusing, but it will become more simple if we divide it up into 2. And we can divide it by the 2 detectors. So we have the FID, flame ionization detector, which is based on the working principle of having a constant flame where you lit the sample gas into, and depending on the content of the sample gas, if it can be burned off, it will ionize the flame, and we can measure it as a current. The TCD works by comparing the thermal conductivity of our sample with a reference flow. The reference flow is not drawn in here, but it has a continuous stream of reference flow, which is the same as our carrier gas, so it will be alkaline. So, but let's start out by looking at one part at a time. So let's have a look at the FID part. The main thing that happens here is our sample comes in. This is it. Happens all the time. Goes through the column and just out again. And this is, we call it idle mode. Nothing happens until we turn the valve and take a sample, or take an injection as it's called. But I have a small video here which is better at explaining it, so illustrating it. So I'll just run this. So what they're illustrating here is the sample comes in, goes through the sample. Simultaneously we have carrier gas running as here into the column. Now they turn the valve. Now the carrier gas pushes the sample into the column until it's empty, and we can turn back the valve again. So let's go back and have a look at how this functions, how the sample actually goes through the whole GC. So first, in idle mode, let's call it for 0 minutes. The sample goes sample down to the next part, or just out, whatever we want. And as soon as we then take an injection, so at 0 minutes, now a stream of water pushes the sample through into the capillary inlet. The capillary inlet is a splitless inlet. It's not very relevant in our case because we just run it as a splitless inlet, but we do have the possibility of taking small samples or small portions of the samples in various ratios. It can be relevant in different setups or other conditions. But yeah, we shouldn't mind that too much. When we know that all of our sample has left the sample and has come into the column, we can close the valve again. Now we're still pushing gas through here into the column where it's being separated. The first thing that gets through here will be, at least the first thing we can detect with the FID will be CO and then methane. Those are both going to the methanizer, where together with hydrogen are being converted, CO is converted into methane. The methane is just passing through, and it's important to remember that they have already been separated. So first we get the CO. CO leaves and is led into the FID where it's getting burned off and detected as a small current. Then, with not much time difference though, the methane is passed through the methanizer as well. And we could bypass the methanizer before the methane, but the two peaks are so overlapping that it would cause a disturbance in the detection. But the next thing that comes through is the CO2. And we have so much CO2 that it would clog up the methanizer or drain its efficiency over time. So we would rather bypass it. And as we don't need it further on, we can just leave it off. So around here, 4 minutes, we turn it off. And now it just goes from the column directly into the body. What is a bit noticeable as well is that now hydrogen supply is not led directly into the methanizer and into the FID, but it's, as it was before, now it is led directly into the FID. And actually this switching causes the FID flame to go out, and then it automatically turns on again, but this creates a little bit of noise, which you can see as noise peaks. The FID is also supplied with air. It should be clean air. If we use what we would call dirty air, then there would be carbon. The if the air contains oil, let's say if it's from a non-clean compressor, then we would burn that off and therefore continuously, and that would give us a large background of noise. So that's why we use cleaned air, or ideal cases, bottled air. So basically just oxygen and nitrogen mixed. Then after 12 minutes, the method, as it's called, is entered, and we're ready to take a new injection. The word meaning method is simply just a description of the program, you can say, of what different timings you have, both for the valves, but you can also change the way the pressure of the gas flows, all the different parts actually, as well as the oven temperature. So the columns are placed in an oven, and you get different products through faster if you increase the flow rate or if you increase the temperature. It's not easy to know exactly what will happen, but those will also change the shape of the peaks. It's a very complex thing to know how to make these DC methods. Now, the reason we're going for 12 minutes, I can tell that the main peaks we're interested in are actually being detected after something like 5 minutes, 6 minutes. The reason we don't stop it there is because if, let's say, we have a C3 product in the column, and we stop the method after 6 minutes, and that would show up after additionally 2 minutes, and we took a new injection, starting the time over again, then it would show up as what you could call ghost peaks in the next chromatograph. So that's why we need to let it run until we know that all of the different compounds in the sample has actually gone all the way through and into the FID, being burned off. A second and perhaps more practical issue is that in order to separate the methane and the CO, we need low temperature, so there we run at 40 degrees. But if we kept it constant at 40 degrees, it would take a very long time to get C3 products through, and therefore we ramp up the temperature. And then when we know that, okay, now they have almost past the column, we start cooling down again. But we can't stop the method until the oven is cooled down to 40 degrees again and ready to take the next sample. So that's the second reason. Now, let's move on to the next part, the TCD part. This looks a bit different, and the reason for this is that we here have both the column, what used in the FID part, but we also have what's known as a molecular sieve. And that's because in this column, small molecules like CO, hydrogen, and mainly nitrogen, oxygen, are not separated very well. They all go through at almost the same time, independent on flow and temperature and everything else. So we want to separate them further. We do that in this molecular sieve. Now, the molecular sieve is not very good at handling stuff like water vapor or CO2. So we would really like to avoid those getting into the molecular sieve. And the way that's done is this valve configuration, where we then will backflush the first column. And I will show you that in a video we have here. So, same as before, we have the sample coming in, going into the sample loop, and then out again. In this case, just to waste. Then we have two carrier gases. One goes through column 1, in this case back flushing, and the other one just sending the sample through. So now we turn the valve, we see that the sample is being sent into the column. And it's actually been sent to both columns, and now at a certain point we know now here the water almost has gone through column 1. We switch the valve back again. Now column 1 is being back flushed, whereas column 2 in our case the follicular sieve is kept in with flow in the same direction. In this way we can separate what actually enters into the second column. So let's have a look at that actually looks like. So in either mode, the sample comes in, comes from the FID part, but that actually doesn't matter. You can change them around if you want to. It comes in, goes through the sample, same size, and it goes out again. Now we do the injection. Argon is the argon pushes the sample into the first column, and down here into the next column, and then after about 3.7 minutes we do the back flush. Now we know that all the products we're interested in has gone into the molecular sieve and have been retained there, passing through there, and now we can actually back flush the first column again, making sure that it's ready for the next injection. And again, we have to wait until the whole program is ended, or the whole method is ended, after 12 minutes. So, let's look at the combined thing. And perhaps we should just mention that, of course, some of the products we want to detect by the TCD are things we cannot detect in the FID. So, the FID can only detect things we can burn off, whereas the TCD can detect anything. So therefore we use the TCD to detect hydrogen and nitrogen and oxygen. Actually we also detect CO down in the TCD. We don't have any oxygen, I should remember to mention, but we also detect CO both places. And in that way we can also make sure that both detectors actually showing the same amount they should, most likely. If not, there's something wrong. So, but let's have a look at how things are actually running with the whole system. We start at the injection time, running both these valves. Now the sample runs in from the sample, so it's the same sample, the same sample taken from the same gas stream. And now we're running in a time that is, you could say that it's parallel to the process time. So whatever time we talk about here, retention time, the time it takes for the gases to pass through the columns, has nothing to do with our experiment. You should regard this as you take a syringe and take out a sample and analyze it hours later. And that's a common mistake to not regard the two timelines as being separate. So we have our time in the GC, the retention time, and then of course we have our experimental time, you could say. We could stop the experiment now if we wanted to. We have taken our sample. It will not change any or influence any of the results we get from the rest of this analysis in the GC. So, after a minute or so, we close the first valve, Then it took some more minutes, around 3.7 I think, or around 4 minutes. Then we closed the back flush, the TCD channel, and then run the methylizer a little bit later. These two timings are actually kind of connected because it's the same columns, they have the same temperature, the pressure through them are also almost the same. So we know that we should change this valve here when the CO has come through, whereas up here we should change it after the CO has been detected. So there's not much difference in these two. The next thing is actually that here we should turn off the methylizer. And then we're back to idle. Here's the links for some more YouTube videos, some of both the ones we've seen here, there's a few more, and there's a general video. I don't think you should take too long watching it, but I've included the link just so that you can see how a GC looks like. It's not exactly the same as the one we're working with, but just to give you an idea of how can these things look like, and hopefully you will be able to recognize a bit of what I've explained to you here. So the next thing is looking at the data from the GC, and we get these chromatographs, they're called, and here we have signal. For the FID it's in picograms, for the TCD it's in microvolts, and then we get these peaks at different retention times. So this is a time scale, and as the products get through the column, they are being detected, and the amount of sample is given by the area of the peaks. And you can see here we have various peaks, and then we set the GC to integrate all of the peaks, and it creates long lists. So what to do with this list? We need to do three things. We want to know three things. First, we want to be able to identify what a certain peak corresponds to, and we then want to read out the area, and then we want to know what is the concentration of that compound in the sample. Now, if no parameters are changed, so temperature, ramping or constant temperature, and the same with the flow is the same for the method, and it's not changed between two methods, then the same compound will always have the same retention time. So in this case, we get the FID signal, and this is the first thing that comes through. This is the CO peak, and I know that CO will always have a retention time of around 3.9. It can be perhaps slightly more or less, but it's around 3.9. It's not suddenly 4.5 minutes or something. And we know that the area, integrated area, is proportional to the amount of sample or amount of compound in the sample. So in this case, the number of moles of CO in our small sample. So we can write up that the area of the peak X, compound X, equals the concentration in the sample times a calibration constant. And of course we can turn that around if we know the area and the calibration constant, we can get the concentration of an unknown sample. And you will get data files with both the chromatographs but also these tables. You then have to go in and figure out what are the different peaks and what is the concentration in the sample. And you get, there might be split on two different sides. We get both for the signal 1, the FID, and for the TCD. It's the same procedure. So, but how can we know these different things? How can we get the calibration constants? How can we know where the peaks are? Well, luckily we have a calibration gas. The calibration gas is simply just an argon gas mixed with a very low amount of different compounds. of hydrogen, methane, carbon monoxide, carbon dioxide, ethylene, ethane, propylene, and propane. All values that we expect to see when doing electrochemical CO2 reduction on a common catalyst. So I have pointed them in a chromatograph here. So for the FID channel, we start out. The first peak is 0, methane, ethylene, ethane, propylene. So they go up the larger the molecules get. There's some noise as well. It is being integrated by the GC, but you just have to ignore that. And the same goes for the TCD. Here we have hydrogen, we have nitrogen. You should ignore that one. We have CO. You don't need to use the CO, but you should be able to compare the CO between the TCD and the FID channel. Those should be the same, or almost the same. So I think that is the basics of how a GC works and how you look at the data. So good luck.